What if you could look back in time, not just decades or centuries, but billions of years, to witness the very first moments of our universe? The James Webb Space Telescope has done exactly that, acting as a time machine to capture light from the dawn of creation. And what it's revealing is rewriting the textbooks. Picture this: ancient galaxies, older than anyone thought possible, glowing faintly in the void, stars igniting for the first time, their light stretching across the cosmos like a whisper from the past. This isn't science fiction, it's the reality of what Webb has uncovered, and it's changing everything we thought we knew about how the universe began. Think about the sheer scale of this achievement. Light travels fast, but it still takes time to cross the unimaginable distances of space. When Webb detects a galaxy 13.6 billion light-years away, we're not just seeing a distant object, we're staring directly into the past, observing the universe as it was in its infancy. These aren't just snapshots, they're cosmic fossils preserved in the fabric of space-time. And the closer we look, the more surprises we find. Galaxies that shouldn't exist yet, stars burning brighter than physics predicted, structures so vast they defy explanation. Webb isn't just answering old questions, it's uncovering mysteries we didn't even know to ask. So how did we get here? How did humanity build a machine capable of seeing the universe's first breath? The story of Webb is one of audacity, of engineers and scientists pushing the limits of technology to peer deeper into space than ever before. But it's also a story about us. Because every time Webb sends back a new image, it's not just data, it's a glimpse into our own origins. The atoms in your body, the air you breathe, even the screen you're staring at right now, all of it was forged in those ancient stars. This is the legacy Webb is revealing, a universe more wondrous, more chaotic, and more beautiful than we ever dreamed. And what's even more thrilling, we're just getting started. Building a machine capable of peering into the universe's infancy wasn't just about ambition. It was about solving puzzles that had baffled scientists for generations. The James Webb Space Telescope began as a bold idea in the 1990s, a dream to push beyond Hubble's limits and capture light from the very first stars. But turning that vision into reality meant overcoming challenges that would have derailed a lesser team. Take the mirrors, for instance, 18 hexagonal segments coated in gold, each polished to an accuracy of less than 1,000th the width of a human hair. If those mirrors were scaled up to the size of the United States, their imperfections would be no taller than a speed bump. And then there's the sunshield, a 5-layered behemoth as big as a tennis court, designed to unfurl flawlessly in the vacuum of space while keeping the telescope colder than the surface of Pluto. Why go to such extremes? Because the universe's oldest secrets are written in infrared light wavelengths invisible to our eyes, but glowing faintly from the heat of those primordial galaxies. Hubble could only see so far. Its vision stopped where cosmic dust blocked the view. But Webb's infrared eyes cut through that haze like a searchlight in the fog, revealing structures hidden since the cosmos was a toddler. Every component, from its cryocoolers to its microshutters, was engineered to detect whispers of light that had traveled for over 13 billion years. And when it launched on Christmas Day 2021, it wasn't just a telescope ascending into space, it was humanity's most sophisticated time machine, poised to rewrite the story of our origins. The stakes couldn't have been higher. A single misstep, a jammed mirror, a torn sunshield could have doomed the mission, but the team's meticulous preparation paid off. Within months, Webb began transmitting images that defied expectations. Galaxies too mature for their age, black holes growing faster than models predicted, nebulae glittering with the raw materials of new solar systems. Each discovery was a reminder that this wasn't just about technology, it was about curiosity, the relentless human drive to stand on the edge of the unknown and ask, what else is out there? And as Webb continues its mission, one thing is certain. The universe's first chapters hold surprises we're only beginning to uncover. To understand how the James Webb Space Telescope pulls off this cosmic magic trick, we need to talk about light's greatest secret. It's a time traveler. When you gaze at the stars tonight, you're not seeing them as they are right now, but as they were years, centuries, even millennia ago. The farther away an object is, the longer its light takes to reach us. That's why Webb's ability to spot galaxies over 13.5 billion light-years away isn't just about distance, it's about peering directly into the universe's toddler years. But here's the catch: light from those ancient objects doesn't arrive unchanged. As the universe expands, it stretches the wavelengths of that light, shifting it toward the red end of the spectrum, a phenomenon called redshift. Think of it like cosmic aging. The older and more distant the light, the more it's stretched. By the time it reaches us, what began as visible light has faded into infrared, invisible to human eyes. That's where Webb's genius kicks in. Its infrared detectors are fine-tuned to catch these faint whispers, transforming them into vivid portraits of galaxies that existed when the universe was just 200 million years old. And Webb doesn't just see farther, it sees clearer. Traditional optical telescopes like Hubble hit a wall when cosmic dust clouds block their view, but infrared light slips through those veils like sunlight through fog. Suddenly, star nurseries hidden for billions of years come into focus, and the chaotic birthplaces of planets reveal their secrets. Every image Webb captures is a puzzle piece in the universe's origin story, showing us structures so ancient they predate Earth itself. The deeper Webb looks, the stranger the cosmos becomes. Galaxies that should be too young to exist already glow with mature stars. Black holes loom unexpectedly large, as if they grew faster than physics allows. Each discovery forces us to rethink our cosmic timeline, proving the early universe was wilder, more inventive, and more mysterious than we ever imagined. This isn't just astronomy, it's archaeology on the grandest scale, unearthing the universe's first whispers before they fade into silence. The moment the James Webb Space Telescope turned its golden eye toward the cosmic horizon, it shattered our expectations. Among its very first targets were galaxies so ancient they existed when the universe was a mere 300 million years old, a cosmic blink after the Big Bang. But here's what left scientists stunned. These galaxies weren't the faint, disorganized blobs theory had predicted. Instead, they glowed with the crisp spiral arms and dense cores of mature cosmic cities, structures that by all rights should have taken billions of years to form. It's like finding a skyscraper in the middle of the Stone Age. Something's not adding up. What makes these galaxies so baffling isn't just their age, it's their sheer audacity. Some shine brighter than a trillion suns, their light defying the limits of what stars that young should produce. Others stretch across thousands of light years, their vast disks and swirling arms betraying a level of organization that shouldn't exist in a universe still in its chaotic infancy. Current models of galaxy formation rely on a slow, steady dance of gas and gravity, where small clumps merge over eons to build something grand. But Webb's galaxies skip the line, appearing fully formed in a time frame that's left theorists scrambling for explanations. Could dark matter, the invisible scaffolding of the cosmos, have played a bigger role than we thought? Some scientists speculate that pockets of this mysterious substance might have clustered earlier and more densely, accelerating star formation like a cosmic fast-forward button. Others wonder if the early universe operated under different physical rules, with higher gas densities or faster cooling rates that let galaxies assemble at breakneck speed. Then there's the wild card. What if our understanding of time itself in those primordial epochs is incomplete? Every new image from Webb deepens the mystery. One galaxy, dubbed the Sparkler, appears to be surrounded by globular clusters, dense groups of ancient stars that typically take billions of years to form. Yet here they are, twinkling around a galaxy that existed before Earth's continents had even taken shape. Another discovery, a massive galaxy nicknamed the Brick, weighs as much as 100 billion suns, a behemoth that challenges the limits of how quickly matter could have clumped together. This isn't just about rewriting textbooks, it's about reimagining the universe's childhood. If galaxies grew up faster than we ever imagined, what else does that imply about the laws of physics? Could black holes have formed sooner, seeding the cosmos earlier than expected? Might stars have burned hotter and died younger, scattering heavy elements into space before our current timeline suggests? Webb's revelations are peeling back layers of cosmic history we didn't even know were there, proving once again that the universe is far stranger and far more inventive than our boldest theories predicted. And with every fresh observation, the telescope isn't just showing us the past, it's inviting us to question everything we thought we knew about how the story began. Before galaxies painted the cosmos with their sprawling light, before planets took shape around newborn stars, the universe flickered to life with its very first beacon's population, 3 stars. These titans of the early cosmos weren't like the stars we know today. Born from clouds of pure hydrogen and helium, uncontaminated by heavier elements, they burned at temperatures and intensities that defy modern stellar physics. Imagine furnaces so powerful, a single one could outshine an entire galaxy of today's stars. Their lives were short, violent, and cosmically transformative, lasting just a few million years before erupting in cataclysmic supernova that forged the universe's first heavy elements. Webb's hunt for these elusive giants is like searching for cosmic ghosts. Since population 3 stars died billions of years ago, we can't observe them directly. Instead, scientists look for their fingerprints, distinct chemical signatures, or the unique light patterns they would have left behind in the surrounding gas. Some of Webb's deepest infrared images reveal pockets of primordial gas glowing with unexpected intensity, regions where the chemistry matches predictions for the aftermath of these stellar behemoths. Other data shows ancient clouds oddly rich in elements like carbon and oxygen, metals that shouldn't exist unless population 3 stars had already seeded them. The stakes of this search couldn't be higher. These stars weren't just the universe's first light bulbs, they were its first alchemists. When they exploded, they scattered newly forged elements like oxygen, carbon, and iron across the cosmos, ingredients that would later form rocky planets, oceans, and even life itself. Finding them would answer fundamental questions. How quickly did the first stars ignite after the Big Bang? Did they form in isolation or in dazzling clusters? And crucially, how did their death set the stage for everything that followed? One of Webb's most tantalizing clues comes from a galaxy called GNZ11, one of the most distant ever observed. Its light shows a surprising abundance of nitrogen, an element that typically requires multiple generations of stars to produce. Yet this galaxy existed when the universe was barely 400 million years old, far too young for conventional stellar cycles to explain its chemistry. Some researchers think this nitrogen could only come from the explosive demise of a population 3 star, a cosmic breadcrumb leading us closer to the dawn of starlight. Even without definitive proof, Webb's data is reshaping our understanding of this era. The early universe wasn't the slow, gradual place we once imagined. It was a fireworks display of stellar birth and death, with population 3 stars as its brilliant but short-lived performers. Their existence hints at a cosmos far more dynamic in its youth, where the rules of star formation might have been radically different, and if Webb does confirm their presence, it would be like uncovering the universe's original recipe, the moment mere atoms transformed into the building blocks of everything we know. To truly grasp the significance of the cosmic microwave background, imagine the universe not as the vast, star-filled expanse we know today, but as a seething ocean of plasma, a scorching broth of particles so hot that light couldn't travel freely. This was the cosmos just 380,000 years after the Big Bang, a moment when everything changed. As the young universe finally cooled enough for atoms to form, light broke free from its chaotic dance with matter, streaming outward in every direction. That first burst of liberated light is what we now detect as the cosmic microwave background, a faint glow permeating all of space, carrying echoes of creation itself. What makes this ancient light so valuable to scientists isn't just its age, it's the story written in its subtle imperfections. To the naked eye, the CMB appears as a uniform wash of microwave static. But peer closer, and you'll find tiny temperature variations, ripples no larger than 1 part in 100,000. These minuscule fluctuations are cosmic hieroglyphs, encoding the seeds of all future structure in the universe. Denser patches would eventually collapse under gravity, giving birth to the first galaxies, while sparser regions became the great cosmic voids. Without these imperfections, matter would have remained evenly distributed, and the universe as we know it, with its glittering galaxies and swirling nebulae, might never have formed. This is where the James Webb Space Telescope becomes indispensable. While earlier missions like Planck mapped the CMB in stunning detail, Webb's infrared sensitivity allows it to investigate how those primordial ripples translated into the universe's first large-scale structures. By studying ancient galaxies in relation to the CMB's blueprint, Webb acts as a cosmic detective, connecting the dots between theory and observation. Some of its most startling findings suggest that matter clumped together faster and more efficiently than our models predicted, hinting that dark matter or even undiscovered physics might have played a stronger role in shaping the cosmos. One of the greatest mysteries Webb could help unravel involves cosmic inflation, the theory that the universe underwent an exponential growth spurt in the first fraction of a second after the Big Bang. The CMB's pattern of fluctuations serves as a fingerprint of this inflationary period, and Webb's observations are refining our understanding of how rapidly it occurred. Some data even suggests there might have been multiple phases of inflation, or that the process varied across different regions of space. These aren't just academic details, they're clues to whether our universe is one of many in a vast multiverse, each with its own unique physical laws. Yet for all its precision, Webb has also deepened the CMB's puzzles. Certain large-scale anomalies in the background radiation, like the mysterious cold spot spanning billions of light years, defy straightforward explanation. Could these be scars from collisions with other universes, shadows cast by primordial black holes, or simply statistical flukes? Every new observation adds layers to the mystery, reminding us that the universe's first light still holds secrets we're only beginning to decipher. What's truly remarkable is how this faint afterglow, now just 2.7 degrees above absolute zero, serves as both a time capsule and a mirror. It shows us not only where we came from, but how much remains undiscovered. As Webb continues to cross-reference the CMB with the universe's oldest galaxies, it's not just filling gaps in our knowledge, it's revealing how chaos and chance conspired to create a cosmos capable of wondering about its own origins. Black holes weren't supposed to be this brazen. Conventional wisdom told us these cosmic monsters took billions of years to grow, slowly feasting on gas and stars until they reached supermassive proportions. But the James Webb Space Telescope has shattered that timeline, spotting quasars, supermassive black holes blazing with the brightness of 1 trillion suns, when the universe was barely 700 million years old. That's like finding a fully grown blue whale in a toddler's swimming pool. How did these gravitational giants bulk up so fast? The answer might rewrite not just the story of black holes, but of galaxies themselves. One radical theory suggests these early behemoths skipped the usual steps entirely. Instead of forming from dying stars, they could have collapsed directly from enormous clouds of primordial gas, cosmic shortcuts to supermassive status. Picture a gas cloud so dense and massive that gravity crushes it straight into a black hole, no star required. These direct collapse black holes would have started life with a huge advantage, packing thousands of solar masses from birth rather than building up gradually. Webb's detection of ancient quasars with masses billions of times our sun's lends credence to this idea, showing black holes that couldn't have grown so large through ordinary means. But there's an even wilder possibility that some of these black holes weren't born in the young universe at all, but are relics of the Big Bang itself. Primordial black holes, theorized to form from density fluctuations in the universe's first chaotic moments, could have served as ready-made seeds. These ancient survivors might have lurked in the cosmic background until galaxies began to form, providing a head start for quasars to reach staggering sizes. If Webb finds black holes even older than the galaxies hosting them, it could be smoking gun evidence for this exotic origin story. What's undeniable is how deeply these early black holes shaped their surroundings. Quasars don't just sit quietly, their ferocious energy output can heat surrounding gas to millions of degrees, halting star formation or even ejecting material entirely. Some theories suggest they acted as cosmic regulators, preventing galaxies from growing too large too quickly. Others argue they were catalysts, their intense radiation triggering waves of star birth. Webb's observations are already revealing quasars embedded in surprisingly mature galaxies, hinting at a feedback loop where black holes and their hosts grew in lockstep. The implications stretch far beyond astrophysics textbooks. If supermassive black holes could form through multiple pathways, it suggests the early universe was far more dynamic and far stranger than we imagined. Their existence challenges our understanding of gravity, time, and the very limits of cosmic growth. With every new quasar Webb discovers, we're not just uncovering black hole origins, we're glimpsing the rulebook of the cosmos itself, written in the violent infancy of spacetime. And the deeper we look, the clearer it becomes. The universe's first monsters still have secrets to spill. Dark matter has always been the universe's silent architect, an invisible hand shaping the cosmos from behind the curtain. But the James Webb Space Telescope is finally pulling back that curtain, revealing how this mysterious substance orchestrated the universe's first structures. Without dark matter's gravitational scaffolding, galaxies as we know them wouldn't exist. Its pull acted like cosmic Velcro, gathering sparse hydrogen gas into dense clouds where stars could ignite. And now, Webb's razor-sharp infrared vision is showing us something startling. Dark matter might not have behaved the way our models predicted in those early epochs. Take Webb's discovery of those surprisingly mature galaxies from just 300 million years after the Big Bang. Their orderly spirals and dense cores suggest dark matter was clustering more efficiently than anyone anticipated. Current simulations assume dark matter particles move sluggishly, forming halos gradually over billions of years. But what if some dark matter was stickier or more interactive in the primordial universe? Certain theories propose that dark matter particles might have collided or exchanged forces in ways that helped structures coalesce faster, like a cosmic fast-forward button pressed during the universe's opening act. Webb's ability to map ancient galaxy distributions provides our first real test of these ideas. By analyzing how these early galaxies clumped together, scientists can trace the invisible dark matter filaments connecting them, a cosmic web woven when the universe was a fraction of its current age. Some patterns already defy expectations. One region in Webb's deep field images shows galaxies aligned along a filament stretching over 13 billion light-years, a structure so vast it hints at dark matter organizing on scales we never thought possible so soon after the Big Bang. Then there's the puzzle of dark matter's temperature. Most models assume it was cold, slow-moving enough for gravity to easily clump it. But Webb's images of faint, diffuse galaxies from the cosmic dawn suggest some dark matter might have been warmer, its particles moving fast enough to resist collapsing into smaller structures. This could explain why we see fewer dwarf galaxies in the early universe than simulations predict, a discrepancy that's haunted astronomers for years. Perhaps most intriguing are the outliers galaxies that appear to be missing dark matter entirely. A handful of Webb's ancient specimens rotate too slowly for their visible mass, as if the invisible glue binding them is oddly absent. Could dark matter have been distributed unevenly in patches, or do these galaxies represent a rare class where normal matter somehow outpaced dark matter's pull? Each possibility forces us to reconsider dark matter's fundamental nature. What's becoming clear is that dark matter wasn't just a passive backdrop to cosmic evolution. It was an active participant, shaping the universe's growth spurt in ways we're only beginning to decode. Every galaxy Webb discovers from this era carries encoded clues about dark matter's behavior, its fingerprints preserved in the spacing, shapes, and motions of stars born when time itself was young. And as we piece together this evidence, we might not just solve the riddle of dark matter, we could uncover entirely new chapters in the story of how order emerged from chaos. Imagine waking up in a world where the air itself is so thick with fog that light can barely travel a few feet before fading into nothingness. That was our universe for hundreds of millions of years after the Big Bang, a vast, murky sea of neutral hydrogen gas where light moved like a car struggling through a blizzard. Then something extraordinary happened. A cosmic dawn broke, not with sunlight, but with the first blazing stars and galaxies, their intense radiation stripping electrons from hydrogen atoms in a process called reionization. Suddenly, the fog lifted, and light could race across the cosmos unimpeded. This pivotal moment transformed the universe from an opaque void into the transparent, star-filled expanse we know today, and the James Webb Space Telescope is uncovering clues about how it happened that are turning old assumptions on their head. For decades, scientists believed reionization unfolded gradually, taking hundreds of millions of years as early galaxies flickered to life one by one. But Webb's observations suggest a far more dramatic rewrite. Some of the telescope's deepest infrared images reveal galaxies pumping out torrents of ultraviolet radiation when the universe was just 200 million years old, far earlier than models predicted. These aren't just isolated beacons, they're part of a sprawling cosmic network, their collective energy ionizing hydrogen at breakneck speed. It's as if we thought the universe turned on the lights with a dimmer switch, only to discover it slammed them on with a thunderclap. What's even more surprising is the sheer efficiency of this process. Reionization didn't just depend on starlight. Supermassive black holes likely played a starring role. Webb has spotted quasars from this era blasting out jets of energy powerful enough to carve ionization bubbles billions of light-years wide. Picture these black holes as cosmic blowtorches, burning tunnels through the hydrogen fog and accelerating the universe's transformation. Some regions may have reionized completely while others lagged behind, creating a patchwork of light and shadow that Webb's detailed spectral analysis is only now beginning to map. Yet mysteries remain. If reionization happened so quickly, why didn't those early photons get absorbed by the densest gas clouds before they could do their work? One provocative theory suggests dark matter might have helped, its gravitational pull funneling hydrogen into filaments that left open pathways for radiation to spread. Another puzzle comes from Webb's detection of helium ions mixed in with the hydrogen, evidence that some unknown energy source, perhaps even exotic particles from the Big Bang's aftermath, added extra heat to the cosmic soup. This isn't just a story about ancient light. Reionization set the stage for everything that followed. Without it, galaxies would have remained shrouded in mist, their light trapped and distorted. Stars might have formed differently or not at all. The very transparency of space today, the fact that we can peer billions of years into the past with telescopes like Webb, traces back to this chaotic, transformative era. And as Webb keeps probing deeper, each new data point brings us closer to understanding how a universe born in darkness became a canvas for the light of countless suns. The cosmic dawn wasn't just a moment, it was the spark that ignited the universe as we know it. The universe's first chemistry experiment began with just two ingredients, hydrogen and helium, the only elements forged in the Big Bang's fiery aftermath. For hundreds of millions of years, these simple atoms drifted through the cosmos, waiting for conditions to cool just enough to bond. Then, in the cold depths of space, something remarkable happened. The first molecules formed. Not the complex chains of carbon-based chemistry we associate with life, but humble pairings like molecular hydrogen, two hydrogen atoms clinging together in the darkness. This was the universe's first step toward chemistry, and the James Webb Space Telescope has now caught these primordial reactions in action, uncovering traces of molecules that existed when the cosmos was barely 1 billion years old. What Webb found upended expectations. Instead of just simple hydrogen molecules, its infrared spectrograph detected the fingerprints of more complex compounds, carbon monoxide, water, even polycyclic aromatic hydrocarbons, the multi-ringed structures that serve as building blocks for everything from DNA to diesel fuel. These molecules shouldn't have existed so soon after the Big Bang. Their presence suggests cosmic chemistry didn't proceed in slow, predictable steps, but in explosive bursts, as if the universe couldn't wait to start cooking up the ingredients for life. The secret to this rapid chemical evolution lies in the hearts of the first stars. When these massive, short-lived giants exploded as supernova, they didn't just scatter heavier elements like carbon and oxygen, they created shockwaves that compressed surrounding gas, triggering chemical reactions in turbulent stellar nurseries. Webb's observations reveal these element-enriched clouds glowing with molecular signatures, proving that the debris of dead stars became the raw material for new chemistry. Some of these clouds show surprising complexity, with organic molecules forming on the surfaces of dust grains, like frost crystallizing on a window pane. But the real shock came when Webb peered at ancient quasars, supermassive black holes surrounded by swirling disks of gas. Their spectra revealed molecules like formaldehyde and methanol, compounds that typically require liquid water to form. How could these exist in the radiation-blasted environments near black holes? One theory suggests these molecules assembled in the relative calm of icy dust grains, protected from the quasar's fury until they were blasted into space by jets of particles. Another possibility is that the intense pressure near black holes created unique conditions for molecule formation, like cosmic pressure cookers accelerating chemistry that would normally take eons. This changes everything we thought we knew about life's cosmic timeline. If complex organic molecules were already widespread when the universe was less than 10% of its current age, the raw materials for biology existed almost from the start. Webb's data shows these molecules weren't rare curiosities. They were everywhere, woven into the fabric of early galaxies like threads in a tapestry. Some even appear in regions with no visible stars, hinting at unknown processes that could spread chemistry far beyond stellar nurseries. The implications are staggering. Life's ingredients didn't have to wait for generations of stars to live and die. They were present at the cosmic dawn, waiting for planets to form and water to flow. Every atom in your body, every molecule that makes up Earth's oceans and atmosphere, traces back to these primordial reactions. Webb isn't just showing us the universe's first chemistry set, it's revealing how the cosmos laid the groundwork for life billions of years before our solar system even existed. And with each new observation, we're getting closer to answering the ultimate question. Was this chemical generosity inevitable, or did we win the cosmic lottery? Galaxies in the early universe didn't grow up in solitude, they thrived through chaos. The James Webb Space Telescope's razor-sharp vision has revealed a cosmic demolition derby where young galaxies crashed, tangled, and merged at a pace we never imagined. In one stunning image, two spiral galaxies stretch toward each other like dancers mid-embrace, their arms warped by gravitational tides, their cores blazing with newborn stars. This wasn't a rare event, it was the norm. While today's universe feels vast and mostly empty, the ancient cosmos was a crowded, frenetic place where galactic collisions happened 5 to 10 times more frequently than they do now. These mergers weren't just spectacular to witness, they were galactic growth spurts. When two galaxies collided, their gas clouds smashed together like storm fronts, compressing hydrogen into dense knots where stars ignited by the millions. Webb's infrared eyes catch these stellar firework displays in action, spotting galaxies producing stars 1,000 times faster than our Milky Way does today. Some of these merger-fueled bursts were so intense they should have blown apart their host galaxies, yet somehow the structures held. The secret might lie in dark matter's invisible grip, whose gravitational scaffolding kept these stellar factories from flying apart even as they burned at full throttle. But the real surprise is how efficient these mergers were at building galactic giants. Take the Sparkler Galaxy, one of Webb's most famous discoveries. Its distorted shape and surrounding globular clusters suggest it's already absorbed multiple smaller galaxies, a process we thought took billions of years longer. Other images show galaxies with bizarre, lopsided jets of stars' telltale debris trails from recent collisions. These findings hint that mergers didn't just accelerate galaxy growth, they might have been the primary engine, assembling cosmic metropolises in a fraction of the time our models predicted. Here's where things get even stranger. Some of these merged galaxies appear to have supermassive black holes at their cores, black holes that shouldn't have had time to grow so large. One leading theory suggests that when galaxies collided, their central black holes merged too, creating gravitational behemoths almost overnight. Webb's detection of quasars in freshly merged galaxies supports this idea, showing how chaos on a galactic scale could forge the universe's most extreme objects far earlier than anyone dreamed possible. What does this mean for our own Milky Way? Its serene spiral arms might be the calm after an ancient storm. By studying these primordial mergers, Webb is piecing together a family album of galactic evolution, one where violence and creativity went hand in hand. Every star we see today, every planet, every ingredient for life, owes its existence to those early cosmic crashes. the universe didn't build itself gently. It grew through collisions, its history written in the twists of starlight and the echoes of long-ago impacts we're only now beginning to decode. One of the most perplexing puzzles in modern cosmology isn't about distant galaxies or ancient stars. It's about numbers that stubbornly refuse to match. The Hubble Tension, as scientists call it, represents a glaring discrepancy in how fast the universe is expanding. Measurements from the Hubble Space Telescope, based on observations of nearby stars and supernova, suggest one expansion rate. But when we look at the afterglow of the Big Bang, the cosmic microwave background, the math points to a significantly slower pace. Enter the James Webb Space Telescope, whose razor-sharp infrared vision has now thrown gasoline on this cosmic controversy by confirming Hubble's numbers with unprecedented precision. This isn't just a minor accounting error. The expansion rate, known as the Hubble constant, is the yardstick by which we measure the age, size, and ultimate fate of the cosmos. If two of our most trusted methods for calculating it disagree by nearly 10%, something fundamental in our understanding of physics might be broken. Some theorists suggest dark energy, the mysterious force accelerating cosmic expansion, could be changing strength over time, growing more potent as the universe ages. Others speculate we might be missing entire ingredients in our cosmic recipe, like undiscovered particles or forces that influenced the early universe's behavior. What makes Webb's role so critical is its ability to cross-examine both sides of this debate. By observing Cepheid variable stars, cosmic mile markers used to gauge distances, with 50 times the clarity of Hubble, Webb has eliminated measurement errors that once clouded the picture. Its verdict, the nearby universe's expansion rate, holds firm, deepening the mystery of why early and modern measurements diverge. But Webb isn't stopping there. Its observations of the cosmic dawn could reveal whether the laws of physics operated differently when the universe was young, a possibility that would rewrite textbooks from the ground up. The stakes couldn't be higher. If the tension persists, we might be staring at the next Copernican revolution, a realization that our cosmic model, however elegant, is missing a crucial piece. Every new dataset from Webb tightens the screws on this puzzle, forcing us to confront whether we've misunderstood gravity, misjudged dark energy, or overlooked something even more profound. The universe is showing us its cards, and the hand we're seeing defies all expectations. One thing's certain: the solution, when it comes, won't just resolve a scientific debate, it will redefine our place in the cosmos. The James Webb Space Telescope has pulled back the curtain on cosmic fireworks from the universe's wild youth, supernova so ancient they detonated when the cosmos was barely a toddler. These aren't your average stellar explosions. Imagine a detonation 100 times more powerful than anything in our modern universe, blasting out shockwaves that traveled millions of light years, seeding the void with the first sprinklings of heavy elements. Webb's infrared detectors have spotted their faint afterglows, remnants of explosions so distant their light has traveled for over 13 billion years to reach us. What makes these primordial supernovas special isn't just their age, it's their staggering violence. Without heavier elements to regulate their nuclear fusion, the first generation of stars burned hot and fast, collapsing in hyper-energetic blasts called pair instability supernova. These cosmic bombs didn't just fade away, they annihilated themselves completely, leaving no black hole or neutron star behind, just an expanding cloud of freshly forged metals. Webb's spectrographs have detected the chemical fingerprints of these events in ancient gas clouds, unusual concentrations of elements like silicon, magnesium, and even traces of gold, all cooked up in single, catastrophic stellar deaths. The most tantalizing clues come from supernova that don't match any modern category. Some show bizarre light curves, their brightness fading in unexpected patterns, while others leave behind chemical signatures with puzzling gaps in certain elements. These anomalies could be our first indirect evidence of population 3 stars, those mythical first-generation giants made purely of hydrogen and helium. If confirmed, it would solve a decades-old mystery. How did these theoretical stars live, die, and transform the chemistry of the early cosmos? But these explosions weren't just destructive, they were creative forces. Every atom of oxygen in your lungs, every speck of calcium in your bones, every fleck of iron in your blood was forged in supernova like these. Webb's observations reveal how these elements didn't spread evenly. They pooled in cosmic eddies and currents, creating chemical islands where future stars would form with richer elemental diversity. Some galaxies from this era show pockets of surprising complexity, with carbon and oxygen abundances suggesting multiple generations of stars had already lived and died in rapid succession. The implications stretch far beyond astronomy. These ancient supernovae set the stage for everything that followed. Without their elemental alchemy, rocky planets couldn't form, water couldn't exist, and life as we know it would lack its essential ingredients. Webb's ability to study these explosions across different cosmic epochs is like watching the universe grow up in fast forward, revealing how chaos and destruction ultimately built the diverse, element-rich cosmos we call home today. And with every new supernova remnant it analyzes, Webb isn't just studying the past, it's uncovering the origin story of the very stuff we're made of. Picture the universe not as a scattering of isolated islands, but as a vast, interconnected network, a cosmic nervous system with threads of gas and dark matter stretching billions of light years between galaxies. These are the filaments of the cosmic web, the hidden scaffolding upon which everything we see is built. And for the first time, the James Webb Space Telescope is pulling them into sharp focus, revealing structures so ancient they existed when the universe was just a fraction of its current age. What Webb has found defies expectations. These filaments, some as wide as 60 million light-years, aren't just passive highways, they're dynamic rivers of matter, funneling gas into galaxies like cosmic conveyor belts. One particularly striking filament, spotted in Webb's deep field images, connects a cluster of young galaxies like beads on a string, its dark matter backbone invisible but betrayed by the way it bends the light of more distant objects behind it. The sheer scale is staggering. If our Milky Way were a grain of sand, this filament would be the length of a football field. But here's the twist: some of these filaments appear too mature for their age. According to simulations, such vast structures should have taken billions of years to form through the slow pull of gravity. Yet Webb shows them fully formed when the universe was less than 2 billion years old. This suggests dark matter might have clumped together far faster than our models predicted, or that unknown forces in the early universe accelerated their growth. One theory even proposes that quantum fluctuations in the first moments after the Big Bang imprinted these patterns onto spacetime itself, like wrinkles frozen into the fabric of the cosmos. The cosmic web isn't just a curiosity, it's the universe's architectural blueprint. Where filaments intersect, galaxies form in dense clusters, while the voids between them remain eerily empty. Webb's ability to trace these structures back to their infancy is revealing how they shaped galactic evolution. For example, galaxies nestled along filaments show more orderly rotation and faster star formation than those adrift in the voids, as if the web itself provided a nurturing environment for cosmic growth. Perhaps most astonishing are the filaments' chemical fingerprints. Webb's spectrographs have detected heavy elements like oxygen and carbon woven into these primordial threads, elements that could only have been forged in the hearts of the first stars and then blasted into intergalactic space by supernova. This means the cosmic web didn't just guide galaxy formation. It also served as the universe's recycling system, distributing the building blocks of planets and life far beyond their birthplaces. As Webb continues to map this hidden skeleton, each new image adds depth to an extraordinary realization. The universe didn't grow randomly. It organized itself with precision, following patterns written into the laws of physics at the dawn of time. And those patterns, invisible to our eyes but now revealed in infrared, are the reason we're here to ponder them at all. Exoplanets weren't supposed to exist this early in the cosmic story. Conventional wisdom held that planets needed generations of stars to live and die, seeding the universe with enough heavy elements for rocky worlds to form. Yet the James Webb Space Telescope has spotted tantalizing evidence of planetary nurseries swirling around stars in galaxies that existed when the universe was barely 5% of its current age-potential exoplanets, dating back over 13 billion years. These aren't just old worlds, they're time capsules from an era when the cosmos itself was still learning how to build planets. The clues come from dust, lots of it. Webb's infrared vision has detected unusual gaps and ripples in protoplanetary disks around ancient stars, patterns that on younger stars would unmistakably signal planet formation. Some disks show concentric rings where newborn planets may be clearing paths as they orbit, while others have asymmetrical bulges suggesting massive worlds tugging at the gas and dust. The most compelling evidence comes from a galaxy called SPT 031158, where one star's disk contains a void nearly as wide as our solar system, a telltale sign that something large and unseen is carving space for itself. This discovery flips planet formation theories on their head. Current models suggest planets need metals elements heavier than hydrogen and helium to clump together into rocky cores. But the early universe was metal poor, with far fewer of these heavy elements available. How could planets form so quickly? One possibility is that the first stars produced metals at astonishing rates, their violent deaths seeding nearby clouds with planet-building material faster than expected. Another theory proposes that giant planets might have formed directly from gravitational instabilities in these primordial disks, skipping the rocky core phase entirely and emerging fully formed from collapsing gas. The implications are staggering. If planets existed in abundance during the cosmic dawn, life's potential timeline stretches back much further than we imagined. Imagine a rocky world orbiting one of those ancient stars, bathed in the ultraviolet glow of a young galaxy. Could life have gained a foothold there? Webb's detection of complex organic molecules in these same early galaxies suggests the ingredients were present. While these primordial planets would have faced harsh conditions, intense radiation, frequent supernova, and unstable orbits, their very existence proves the universe was building worlds almost as soon as it could. What's equally surprising is how different these early planetary systems might have been. Without an abundance of metals, gas giants could have dominated, their massive gravity hoarding material before smaller worlds could form. Some simulations suggest these ancient systems may have contained carbon planets, worlds with graphite crusts and diamond mantles, forged from carbon-rich debris of the first stars. Others might have hosted lava planets so close to their stars that their surfaces were molten oceans, constantly reshaped by tidal forces. Webb's next steps could rewrite astronomy textbooks. By analyzing the atmospheres of these potential exoplanets, if they exist, we might detect gases that reveal their composition and climate. Finding oxygen or methane would be revolutionary, hinting at processes that could support life. But even without biology, these worlds are rewriting history. They prove the universe didn't wait to start assembling planets. It began the moment the first stars flickered to life, setting in motion a chain of events that would eventually lead to us. Every new observation peels back another layer, showing us a cosmos far more inventive and far more eager to build worlds than we ever dreamed possible. The first stars didn't fade quietly into the cosmic night. They went out in explosions so colossal they shaped the universe itself. Born from clouds of pure hydrogen and helium, these stellar pioneers burned at temperatures modern stars couldn't survive, their cores churning like nuclear furnaces under unimaginable pressure. Their lives were brief, just a few million years, a blink compared to our sun's 10-billion-year lifespan, but their deaths were anything but subtle. When these behemoths exhausted their fuel, they didn't just collapse, they detonated with enough force to outshine entire galaxies, seeding the cosmos with the first heavy elements. The James Webb Space Telescope is now hunting for their remains, sifting through the ashes of these primordial explosions to decode the violent end of the universe's first light. Some of these stars met their fate in pair instability supernova, runaway thermonuclear blasts so powerful they left nothing behind: no neutron star, no black hole, just an expanding cloud of newly forged elements. Webb's infrared spectrographs have spotted the chemical fingerprints of these events in ancient gas clouds, bizarrely high concentrations of elements like silicon and magnesium, alongside traces of gold and platinum, metals that could only form in such extreme conditions. Other remnants hint at a different demise. In the heart of certain early galaxies, Webb has detected black holes far too massive for their age, collapsed cores of first-generation stars that may have swallowed their surroundings whole, growing at rates that defy modern astrophysics. But the real treasure lies in the neutron stars, these ultra-dense stellar corpses, no wider than a city yet heavier than the sun, should be littered across the early universe. Some might even exist as magnetars, neutron stars with magnetic fields a quadrillion times stronger than Earth's, capable of bending atoms into needle-thin shapes. Webb's hunt for these exotic relics isn't easy. Neutron stars emit little light unless they're actively feeding or spinning rapidly as pulsars. Yet in a handful of distant galaxies, astronomers have spotted flickering X-ray sources that match predictions for ancient pulsars, their beams sweeping across space like cosmic lighthouses from a vanished era. The most surprising finds aren't lone remnants, but entire nebulas glowing with the debris of multiple supernova. One region, catalogued as JWST 13-0, shows concentric shells of gas rich in oxygen and carbon, evidence of successive stellar explosions piling material into space like layers of an onion. These chemical time capsules reveal how quickly the universe recycled its first ingredients, turning the ashes of dead stars into the building blocks for new ones. Without these violent deaths, the cosmos would have remained a sterile void of hydrogen and helium, never forging the elements needed for planets or life. What Webb is uncovering isn't just a graveyard of ancient stars, it's a chronicle of cosmic reinvention. Every black hole, neutron star, and enriched nebula tells a piece of the story, how the first generation of stars lived fast, died young, and in their destruction laid the foundation for everything that followed. Their remnants are more than relics, they're the universe's first alchemists, transforming simplicity into complexity, chaos into order. And as Webb peers deeper into the past, each discovery brings us closer to answering the ultimate question: how did we get from the Big Bang's fiery aftermath to a cosmos brimming with worlds? The answer, it seems, was written in the deaths of the very first stars. Gravity doesn't just pull, it magnifies. When the James Webb Space Telescope stares into the cosmic abyss, it's not working alone. Some of its most breathtaking discoveries come courtesy of nature's own telescope, gravitational lensing, a phenomenon where massive galaxy clusters warp the fabric of space-time so profoundly that they bend light like a prism. These cosmic lenses amplify the faint glow of galaxies so distant they'd otherwise be invisible, stretching their light into luminous arcs and smears that resemble celestial mirages. And it's through these warped windows that Webb has glimpsed galaxies as they existed a mere 200 million years after the Big Bang, objects so ancient they predate Earth by over 13 billion years. The magic lies in Einstein's theory of relativity. Just as a glass lens bends light to focus it, a galaxy cluster's immense gravity distorts the path of light from objects behind it, acting like a magnifying glass for the universe's most distant treasures. One of Webb's most stunning examples is the galaxy cluster SMACS 0723, whose gravitational grip transforms background galaxies into stretched, mirrored crescents, some replicated multiple times across the same image like reflections in a funhouse mirror. Without this natural amplification, these galaxies would be little more than faint smudges, their secrets lost to the void. But gravitational lensing isn't just about zooming in, it's about cosmic archaeology. The distortions themselves reveal hidden details about both the lens and the lensed. By analyzing how light bends around foreground clusters, scientists can map the distribution of dark matter within them, uncovering the invisible scaffolding that shapes the universe. Meanwhile, the magnified background galaxies offer pristine snapshots of the early cosmos, their stretched light providing spectral fingerprints of their composition, temperature, and motion. One lensed galaxy, nicknamed the Sparkler, appears dotted with globular clusters, dense groups of stars that shouldn't have had time to form so soon after the Big Bang. Yet there they are, glittering like diamonds strung along a cosmic necklace. The real power of this technique lies in its serendipity. Unlike human-made telescopes, gravitational lenses can't be pointed. They're chance alignments of mass and light. But when nature cooperates, the results are staggering. In Webb's deep field images, some lensed galaxies appear 10, even 50 times brighter than they would otherwise, their light twisted into delicate Einstein rings, perfect circles of warped starlight predicted by relativity over a century ago. These rings aren't just beautiful, they're cosmic measuring tapes, allowing astronomers to calculate precise distances to galaxies at the edge of observable time. What's truly mind-bending is how lensing unveils galaxies that defy expectations. Some appear smaller yet more massive than models predict, their stars packed into tight, brilliant knots. Others show spiral structures so refined they challenge theories of how quickly order emerged from the primordial chaos. And a few, magnified by multiple clusters in a phenomenon called double lensing, reveal details as fine as individual star-forming regions, a view of the universe's toddler years with unprecedented clarity. This partnership between human ingenuity and natural phenomena is rewriting cosmic history. Every lensed galaxy Webb studies is a two-for-one discovery, a glimpse into the distant past and a lesson in the gravitational ballet that structures our universe. And as Webb continues to harness these celestial magnifying glasses, each new image proves that sometimes the universe itself provides the best tools for uncovering its deepest secret if we know how to look. Quasars should have been latecomers to the cosmic party according to most theories. Supermassive black holes needed billions of years to grow by slowly feasting on gas and stars. Yet the James Webb Space Telescope keeps finding these brilliant beacons shining fiercely when the universe was less than 700 million years old, their light so intense it outshines entire galaxies. One quasar in particular, J1342+0928, weighs as much as 1.6 billion suns, a gravitational monster that by all rights shouldn't have existed before the cosmos hit its teenage years. The mystery isn't just their size, it's their appetite. These ancient quasars devour matter at rates that defy physics as we know it, consuming the equivalent of a sun's worth of material every day. Webb's infrared spectrographs have caught them in the act, detecting the telltale glow of superheated gas swirling at near light speeds before vanishing across their event horizons. But here's the puzzle. Even at maximum cosmic calorie intake, there's no way these black holes should have reached such staggering masses so quickly. Something gave them a head start, and astronomers are racing to figure out what. One radical idea suggests these black holes didn't grow from the ground up at all. Instead, they might have formed ready-made, collapsing directly from gargantuan clouds of primordial gas in the universe's first chaotic moments. Picture a gas cloud so dense and massive that gravity bypasses the star-forming stage entirely, crushing it straight into a black hole with thousands of solar masses from birth. Webb's observations lend credence to this theory, spotting quasars embedded in galaxies that show oddly pristine gas reservoirs, exactly what you'd expect if the central black hole had formed without the usual stellar fireworks. But there's a wilder possibility. These black holes might be relics of the Big Bang itself. Tiny fluctuations in the newborn universe's density could have created microscopic black holes, some no heavier than an asteroid, that then gorged on the abundant gas of the cosmic dawn. Over hundreds of millions of years, the largest of these seeds could have snowballed into the quasars Webb now sees. Supporting this idea are odd gaps in some quasars' light spectra, hints that their surroundings might contain leftover pockets of primordial gas untouched by later star formation. What's undeniable is how these quasars transformed their cosmic neighborhoods. Their blistering radiation ionized hydrogen gas across millions of light years, clearing the fog of the early universe and making space transparent to light, a process called reionization that shaped everything that followed. Webb's ability to study quasars at multiple stages of this epoch is like watching a time lapse of cosmic history, revealing how the brightest objects in existence also served as the universe's first lighthouses, guiding the evolution of galaxies around them. Yet for all their brilliance, quasars raise more questions than answers. Why do some early galaxies host quasars while others seemingly identical have quiet, dormant black holes? Could there have been even earlier quasars whose light hasn't yet reached us? With every new quasar Webb discovers, the boundary of the possible gets pushed further back, forcing us to reconsider how black holes, galaxies, and the cosmos itself grew up together. Their light, traveling for billions of years, is more than a beacon from the past. It's a challenge to rewrite the story of how the universe works. Cosmic inflation wasn't just a gentle stretch, it was the universe's most extreme growth spurt, ballooning from smaller than an atom to the size of a grapefruit in less than a trillionth of a second. This explosive expansion, theorized to explain why the cosmos appears so smooth and uniform on large scales, left behind subtle fingerprints that the James Webb Space Telescope is now decoding. Imagine blowing up a balloon with microscopic wrinkles as it inflates. Those tiny imperfections stretch into vast patterns. That's precisely what inflation did to the quantum fluctuations of the newborn universe, magnifying them into the seeds of galaxies we see today. Webb's observations of ancient galaxies and the cosmic microwave background are putting inflation to the test. One key prediction: the distribution of galaxies should follow a specific statistical pattern, like cosmic confetti scattered with mathematical precision. Early data reveals hints of this signature galaxies clustered at distances that align with inflationary models, their arrangement echoing the primordial ripples frozen into space-time during that hyperactive first moment. But there's a twist. Some galaxy groupings appear slightly more crowded than inflation alone can explain, suggesting additional forces might have been at play during or immediately after this rapid expansion. The telescope's scrutiny of the cosmic microwave background adds another layer. While missions like Planck mapped the CMB's temperature variations in exquisite detail, Webb's infrared eyes can trace how those ancient ripples translated into actual structures. By comparing the CMB's blueprint with the distribution of galaxies from the cosmic dawn, scientists are checking whether inflation's predictions hold across billions of years. One tantalizing mismatch has emerged. Certain large-scale patterns in the CMB, like the mysterious cold spot, don't align perfectly with galaxy distributions. Could this mean inflation wasn't uniform? Some theorists speculate that the early universe might have undergone multiple phases of inflation, each leaving distinct marks on the cosmos. Confirming inflation wouldn't just validate a theory, it would reveal the universe's birth certificate. If Webb detects gravitational waves imprinted on the CMB, it would be smoking gun evidence for inflation's violent energy release. These ripples in space-time, predicted to polarize light in a specific pattern, are the universe's first tremors, carrying information from a time before atoms existed. While no telescope has spotted them yet, Webb's precision measurements of galactic motions and the CMB's finer details are narrowing the search, ruling out alternative theories that don't involve such rapid expansion. Yet the most exciting possibility is that inflation wasn't the end of the story. Some models suggest our universe is just one bubble in a vast multiverse, with other bubbles inflating under different physical laws. Webb's ability to spot anomalies, regions where matter clumps oddly or primordial light behaves unexpectedly, could hint at collisions between our bubble and others, like cosmic fingerprints on a window between worlds. Whether confirming inflation or uncovering its surprises, Webb isn't just studying the past, it's probing the very rules of reality, revealing how a fleeting moment of unimaginable growth set the stage for everything that followed. We know the universe is made of dark energy, dark matter, and ordinary matter, but here's the cosmic twist: half the ordinary matter is missing, not hidden, not transformed, just gone without a trace. These lost particles, called baryons, are the building blocks of everything we see: protons, neutrons, the atoms in your body, and the stars above. Yet when astronomers tally up all the visible matter in galaxies, stars, and gas clouds, it accounts for barely half of what the Big Bang's leftover light tells us should exist. The James Webb Space Telescope has joined the hunt, turning its infrared gaze toward the faint, superheated gas filaments of the cosmic web, where theorists believe these elusive baryons have been hiding for billions of years. The challenge isn't just finding them, it's seeing them at all. These missing baryons aren't clumped into galaxies or cold enough to emit visible light. Instead, they're thought to linger as diffuse plasma, 1,000,000 degrees hot but so thin that a cube of it the size of Earth would contain barely a few atoms. Webb's secret weapon, its ability to detect subtle distortions in the light of distant quasars as it passes through these invisible filaments. Like spotting a fingerprint on a glass window, Webb analyzes how the gas imprints specific wavelengths onto background light, revealing not just the baryons' presence but their temperature, density, and even their motion through space. One of Webb's most startling discoveries so far involves a filament stretching between two galaxy clusters, where the telescope detected the telltale absorption signatures of highly ionized oxygen, a tracer for baryon-rich gas. The filament's mass matched predictions perfectly, suggesting these cosmic threads might be the universe's lost matter reservoir, but the real surprise came when Webb mapped their distribution. Instead of being smoothly spread, the baryons clumped in unexpected knots and voids, as if the cosmic web had a texture no simulation predicted. This could explain why some galaxies grew so quickly. They might have been seeded in baryon-dense regions, fed by rivers of hot gas flowing along these invisible highways. The implications go beyond bookkeeping. If most ordinary matter exists as intergalactic plasma, it means galaxies aren't isolated islands, they're nodes in a vast, dynamic network, constantly exchanging matter and energy with their surroundings. Some of the gas Webb detects may have been ejected from galaxies eons ago by supernova winds or black hole jets, only to cool and fall back in later, fueling new generations of stars. Other filaments could be pristine, never having collapsed into galaxies at all fossils of the universe's initial conditions. Solving the missing baryon problem would do more than balance the cosmic ledger. It would reveal how matter flows across the universe, connecting the dots between the Big Bang's aftermath and the richly structured cosmos we see today. Every filament Webb traces, every wisp of gas it detects, brings us closer to understanding why some regions of space became glittering cities of stars while others remained dark and empty. The answer might lie in those vanished atoms, the universe's hidden scaffolding, finally coming into view. Neutrinos are the universe's shadowy spectators, particles so elusive they pass through entire planets as if they weren't there. Born in the unimaginable heat of the Big Bang, trillions of these ghostly particles streamed through every cubic inch of the early cosmos. Their presence felt more through their absence than their interactions. Yet despite their reluctance to engage with ordinary matter, neutrinos may have played a quiet but pivotal role in sculpting the universe's large-scale structure. The James Webb Space Telescope is now searching for their fingerprints in the ancient patterns of galaxy clustering, hunting for subtle distortions that could reveal how these nearly massless particles shaped cosmic evolution. What makes neutrinos so fascinating isn't just their stealth, it's their paradoxical influence. Though each neutrino carries vanishingly little mass, their collective gravitational pull in the early universe could have acted like a cosmic sieve, smoothing out matter density fluctuations on the smallest scales. Picture a river flowing over a bed of pebbles. The water neutrinos doesn't stop the pebbles' matter clumps from settling, but it determines how they arrange themselves. Webb's ultra-deep galaxy maps are revealing unexpected gaps and clustering patterns in the cosmic web anomalies that align eerily well with simulations where neutrinos slightly suppress the growth of dwarf galaxies while allowing larger structures to flourish. The smoking gun would come from timing. Neutrinos travel at nearly the speed of light, meaning they raced ahead of slower-moving dark matter and baryons in the universe's youth. This created a lag between where neutrinos were and where matter could collapse, leaving a telltale offset in the distribution of galaxies. Webb's ability to pinpoint galaxy positions with unprecedented accuracy across different cosmic epochs lets astronomers check for this delay, like finding two sets of footprints in the sand, one slightly ahead of the other. One preliminary study of a galaxy cluster from when the universe was just 2 billion years old shows a peculiar void in its outskirts, a possible neutrino shadow, where these particles' early departure thinned out nearby matter. But the real prize lies in neutrino mass. For decades, physics has known neutrinos have mass, just not how much. Even a tiny difference in their weight would dramatically alter how they sculpted the cosmos. Webb's observations of ancient galaxy clusters could settle the debate. If neutrinos are lighter, their smoothing effect would be more uniform. If heavier, they'd leave patchier, more pronounced voids. Already, some data suggests neutrinos might be slightly more massive than lab experiments indicate, a hint that their properties could change over cosmic time or in extreme environments. The implications stretch far beyond astronomy. Neutrinos are the only known particles that require physics beyond the standard model to explain their behavior. If Webb confirms their role in shaping the universe, It wouldn't just fill a gap in cosmic history, it could point toward undiscovered particles or forces that operated in the universe's first moments. Every anomaly in galaxy clustering, every unexpected void or filament, might be a message from the dawn of time, written in the language of particles that barely interact with anything at all. And as Webb peers deeper into the cosmic past, it's not just mapping galaxies, it's decoding the invisible currents that guided them into being. The idea that our universe might be just one bubble in an infinite cosmic froth has long hovered at the edge of science, too compelling to ignore, yet too speculative to prove. But the James Webb Space Telescope is bringing new evidence to this debate, not by glimpsing other universes directly, that's impossible, but by scrutinizing the peculiarities of our own. Take the Hubble tension, that nagging discrepancy in the universe's expansion rate. Some theorists suggest it could be a fingerprint of neighboring universes gently tugging on ours, their gravity subtly warping space-time in ways Webb's precision measurements might detect. Others point to anomalies in the cosmic microwave background, those strange cold spots and asymmetries, as potential bruises from collisions with other bubble universes in the cosmos's riotous infancy. Webb's most provocative clues come from the early universe's baffling maturity. Those fully formed galaxies and precocious black holes shouldn't exist in such a young cosmos unless conditions at the Big Bang were exquisitely fine-tuned, a tuning some argue is more plausible if countless universes with different physical constants exist, and we simply inhabit the one where everything aligned perfectly for complexity to arise. It's like walking into a room with 1,000 dials set to random values, yet finding every one adjusted precisely to sustain life. The multiverse theory offers an explanation. With infinite universes, every possible configuration becomes inevitable somewhere. Critics counter that these are just imaginative interpretations, that anomalies in Webb's data could have mundane explanations, but the telescope's ability to map the primordial universe in unprecedented detail is forcing even skeptics to confront uncomfortable questions. Why does the distribution of early galaxies show fractal-like patterns that resemble bubble intersections? Could the variations in fundamental constants across different regions of space hinted at in Webb's spectral analyses be echoes of separate inflation zones with slightly different physics? The multiverse remains untestable in the traditional sense, but Webb is probing its shadow. By measuring the universe's flatness to exquisite precision, it's checking whether spacetime could stretch infinitely, a prerequisite for many multiverse models. Its observations of quantum fluctuations frozen into the cosmic microwave background may reveal whether inflationary bubbles left distinctive imprints. And if Webb finds evidence of cyclic universes, cosmic rebounds from prior Big Bangs, it would reshape the debate entirely. What's at stake isn't just the existence of other universes, but the nature of reality itself. If Webb's data keeps defying expectations, we may need to consider that our cosmos isn't the solo performance we imagined, but one act in an endless cosmic play. Until then, every strange galaxy, every inexplicable quasar becomes a clue in history's greatest detective story, one where the answer might lie beyond the edges of spacetime. Alien megastructures sound like science fiction, but the universe has a way of surprising us. Take Tabby's star, for example. This bizarre celestial object dims unpredictably, sometimes by up to 22%, in ways that defy typical explanations like planets or dust clouds. Some scientists have floated the wild possibility that its light is being blocked by artificial structures, perhaps a Dyson swarm, a hypothetical array of solar collectors built by an advanced civilization to harness a star's energy. While natural causes are far more likely, the James Webb Space Telescope is now equipped to investigate such anomalies with unprecedented precision, separating cosmic oddities from potential technosignatures. Webb's infrared capabilities give it a unique advantage in this hunt. Unlike optical telescopes that might miss subtle details, Webb can analyze the exact wavelengths of light being blocked or scattered by mysterious objects. If a star's dimming were caused by a swarm of orbiting megastructures, the telescope could detect the telltale heat signature of absorbed and re-radiated energy, a pattern distinct from natural dust or gas. Already, Webb has examined stars with unusual light curves, ruling out some exotic theories while deepening other mysteries. One star system, nicknamed Boyajian's World, after the astronomer who first noted its erratic behavior, showed infrared excesses that could indicate circumstellar debris, but the data leaves room for questions. The search isn't just about modern alien civilizations. Webb could uncover relics of ancient ones. In a universe 13.8 billion years old, it's plausible that advanced species arose long before Earth even formed. Their megastructures, if they exist, might now be cold and dormant, detectable only as infrared shadows or unusual metallicity in distant star systems. Some theorists suggest scanning globular clusters, ancient stellar cities where civilizations could have had billions of years of head start. Others propose looking for Fermi bubbles, vast regions where a civilization's energy use might have left lasting thermodynamic imprints on the interstellar medium. Of course, extraordinary claims require extraordinary evidence. Most of these anomalies will turn out to have natural explanations colliding planetary debris, rogue cometary swarms, or even exotic physics we haven't yet discovered. But Webb's real power lies in its ability to test these hypotheses rigorously. By analyzing the chemical composition of dust around peculiar stars or mapping the thermal profiles of unexplained dimming events, it can chip away at the uncertainty. Even if the telescope never finds proof of alien engineering, the process of elimination will sharpen our understanding of cosmic phenomena that once seemed inexplicable. What makes this search so compelling isn't just the remote chance of discovering ET, it's the reminder that the universe is stranger than we imagine. Whether uncovering new types of celestial objects or ruling out the wildest theories, Webb is expanding the boundaries of what we consider possible. And somewhere in that vast cosmic archive between the ancient galaxies and the newborn stars, there might just be a clue that changes everything. For all its revolutionary power, the James Webb Space Telescope isn't all-seeing. There's a fundamental wall it can't peer beyond. The universe's earliest moments remain hidden behind an impenetrable curtain of primordial plasma. In those first 380,000 years after the Big Bang, space was so dense and hot that light couldn't travel freely. Photons bounced endlessly between charged particles, trapped in a cosmic pinball game. No telescope, not even Webb, can observe this murky epoch directly. It's like trying to see through frosted glass smeared with glowing paint. The light from that era only breaks free when the universe cools enough for atoms to form, leaving us forever blind to creation's opening act. Then there's the challenge of cosmic dust. While Webb's infrared vision cuts through much of the obscuring haze that stymied Hubble, certain wavelengths still get absorbed by dense molecular clouds. These interstellar curtains, packed with tiny silicate and graphite grains, block our view of galaxies nestled behind them, like trying to spot a lighthouse through a sandstorm. Some of the most interesting cosmic phenomena, like the cores of starburst galaxies or the inner regions of protoplanetary disks, remain partially veiled. Webb can tease out details by observing at longer infrared wavelengths where dust is more transparent, but even then, some secrets stay stubbornly hidden. Detecting the faintest objects pushes Webb to its limits. The most distant galaxies appear as mere whispers of infrared light. their signals attenuated by 13 billion years of cosmic expansion. Capturing these photons requires exposures lasting dozens or even hundreds of hours, with every minute of observation time fiercely competed for by astronomers worldwide. And even then, some objects are simply too dim, like the hypothetical first stars, which might have formed in small, isolated clusters too faint for Webb to spot individually. The telescope's instruments also face fundamental noise limits from their own electronics and the infrared glow of the solar system's dust, creating an inescapable flaw to how faint a source it can detect. Yet these constraints aren't failures, they're signposts pointing to the next frontiers. Future observatories like the Habitable Worlds Observatory or the Laser Interferometer Space Antenna will extend Webb's legacy, probing gravitational waves from the Big Bang or directly imaging Earth like exoplanets. Ground-based telescopes with 30-meter mirrors will complement Webb's infrared views with razor-sharp optical observations, and ambitious concepts like the Far Infrared Surveyor could map the universe's dust-obscured regions with 10 times Webb's sensitivity, revealing the hidden half of cosmic star formation. The quest to understand our origins has always been a relay race, each generation of telescopes passing the baton to the next. Webb's revelations have rewritten cosmic history, but they've also shown us how much more remains undiscovered. Every limit it encounters isn't an ending. It's an invitation to build something even bolder, to push our vision closer to that elusive first moment when time itself began. The universe's greatest mysteries don't surrender easily, but with each technological leap, we steal another glance across the threshold of creation. The James Webb Space Telescope has rewritten cosmic history, but it's not working alone. Standing on its shoulders are revolutionary new observatories already in development, each designed to tackle mysteries Webb can't fully unravel. Take the Nancy Grace Roman Space Telescope, set to launch in 2027. While Webb zooms in on distant galaxies with stunning precision, Roman will step back to capture the big picture, surveying vast swaths of sky with a field of view 100 times wider than Hubble's. This bird's-eye perspective will map the cosmic web in unprecedented detail, tracing how dark matter's invisible threads have woven galaxies together across billions of years. Its specialized instruments will also study dark energy's accelerating push on the universe's expansion by measuring how galaxy clusters distort light, a phenomenon called weak gravitational lensing that could reveal whether dark energy's strength has changed over time. Then there's LUVOIR, the Large Ultraviolet Optical Infrared Surveyor, a proposed flagship mission that could launch in the 2030s. Imagine a telescope with a mirror nearly 50 feet across, dwarfing Webb's 21-foot primary. With this colossal light-gathering power, LUVOIR would directly image Earth-sized exoplanets in habitable zones, analyzing their atmospheres for biosignatures like oxygen, methane, and water vapor. Its ultraviolet capabilities would let it peer into stellar nurseries obscured to Webb, watching stars being born in violent bursts of radiation that strip electrons from atoms. Where Webb sees the infrared glow of ancient galaxies, LUVOIR could spot their ultraviolet light, the very wavelengths those young stars blazed with before cosmic expansion stretched their light into the infrared. Together, these telescopes would form a time machine spanning the universe's entire history. But the next generation isn't just about bigger mirrors, it's about sharper vision. The Habitable Worlds Observatory, another concept in early planning stages, would combine extreme contrast imaging with advanced coronagraphs to block starlight, revealing planets just 1/10 billionth as bright as their host stars. This technology could finally answer whether life exists beyond Earth by detecting chemical imbalances in exoplanet atmospheres that might indicate biological activity. Meanwhile, far-infrared missions like the Origins Space Telescope would probe colder cosmic phenomena Webb can't see clearly. The frigid dust clouds where complex organic molecules form, or the icy outer regions of protoplanetary disks where comets are born. What makes this new era so transformative is how these telescopes will work in concert. Webb's infrared eyes reveal the universe's first galaxies, Roman maps their large-scale distribution, and Louvre examines their ultraviolet youth. Webb spots potential biosignatures on distant worlds, while the Habitable Worlds Observatory confirms them. Origins studies the chemistry of star-forming clouds that Webb identifies. This isn't just a sequence of missions, it's a symphony of complementary instruments, each playing its part to reveal cosmic truths no single telescope could uncover alone. The questions these observatories might answer are as profound as they are endless. Did life arise elsewhere in the cosmos? What exactly is dark energy, and is it truly constant? How did the first black holes grow so impossibly fast? With each new telescope, we're not just building better instruments, we're constructing new lenses through which to understand our place in the universe. Webb has shown us how much we didn't know. The coming decades promise revelations that will make today's discoveries look like mere previews of the cosmic story still waiting to be told. The moment the James Webb Space Telescope beams back a new image, the internet erupts. Twitter threads multiply like cosmic inflation, Reddit forums ignite with analysis, and Instagram feeds transform into digital planetariums. It's not just astronomers hitting refresh, teachers pause lessons to show students swirling nebulae, artists sketch galaxies onto cafe napkins, and grandparents text grandchildren about black holes. JWST has turned cosmology into a shared human experience, where a single snapshot of a dying star or a distant galaxy cluster becomes a global conversation starter. Remember the debut of the Carina Nebula image. Overnight, its towering gas pillars glowing like celestial skyscrapers became the most famous landscape in the universe, plastered across phone screens from Tokyo to Toronto. But the reactions go deeper than awe. Citizen scientists scour every pixel, sometimes spotting details professionals miss. When an amateur astronomer flagged an oddly distorted galaxy in Webb's deep field image, it led researchers to confirm a rare gravitational lensing event. Online communities dissect spectral data for chemical signatures, debating whether a wisp of methane in an exoplanet's atmosphere could hint at biological activity. Even misinformation gets a cosmic twist. Conspiracy theories about too perfect galaxy shapes or claims of alien megastructures reveal how profoundly these images stir imagination. The telescope's accessibility is deliberate. NASA press releases pair raw science with poetic descriptions, translating light years and redshift into stories of cosmic dawn. Social media teams amplify the drama, posting side-by-side comparisons of Hubble's and Webb's views of the same object, the difference in clarity feeling like swapping binoculars for a microscope. Museums project Webb's images in planetarium domes, letting audiences float through the pillars of creation as if riding a spaceship. And when a teenager's TikTok about quasar shadows goes viral, it proves cosmology no longer belongs solely to academics in white coats. Yet the real magic lies in how these discoveries reframe our place in the universe. A single Webb image can contain thousands of galaxies, each with billions of stars, yet viewers don't feel small, they feel connected. Comment sections fill with existential musings. If stardust made us, are we the universe thinking about itself? or those ancient galaxies died so we could exist. The telescope's greatest gift isn't just data, it's perspective. In an era of division, Webb's portraits of cosmic chaos and beauty offer something rare, a reminder that everyone, everywhere, is literally made of the same stardust, riding the same expanding speck of spacetime. And as long as the images keep coming, that sense of shared wonder will too. Gazing into the cosmic abyss with telescopes like James Webb doesn't just reveal distant galaxies, it holds up a mirror to humanity itself. Every time we peer deeper into the universe's origins, we're forced to confront unsettling questions about our significance. If Webb shows us thousands of galaxies in a patch of sky no larger than a grain of sand held at arm's length, what does that say about our place in the grand scheme? Ancient cultures saw the cosmos as a storybook written for human eyes, but modern astronomy paints a humbler picture. We're not the audience, not the protagonists, just fleeting observers in a drama that began billions of years before us and will continue long after we're gone. Yet this cosmic perspective doesn't have to diminish us. Those same images of swirling galaxies and dying stars reveal something extraordinary. The atoms in our bodies were forged in those ancient stellar furnaces. We're not separate from the universe, we're its conscious embodiment, a way for the cosmos to understand itself. This duality sparks fierce debate. Some argue such discoveries should inspire greater stewardship of our fragile planet, the only home we've ever known. Others counter that focusing on distant stars distracts from pressing earthly crises like climate change or inequality. Why spend $10 billion on a telescope when children go hungry? The tension between exploration and responsibility isn't new. When Renaissance astronomers pointed their crude telescopes at Jupiter's moons, critics accused them of neglecting earthly duties. Yet those same observations eventually revolutionized navigation, timekeeping, and our very conception of reality. Webb's proponents argue its technological spin-offs, from medical imaging to climate modeling, already justify its cost, while its cosmic census guides our search for habitable worlds, an insurance policy against planetary catastrophe. Perhaps the most profound ethical question isn't whether we should look up, but how we balance wonder with wisdom. Discovering 1 trillion galaxies doesn't absolve us from fixing Earth's problems, just as solving poverty wouldn't negate our need to explore. The true legacy of telescopes like Webb lies in their ability to shift our perspective not just outward toward the stars, but inward toward what kind of civilization we aspire to be. A species that only stares at its feet may survive, but one that also lifts its eyes to the cosmos might just find the inspiration to thrive. JWST has peeled back layers of cosmic history like never before, yet with every answer, it uncovers deeper mysteries. Take those impossibly mature galaxies from the universe's toddler years. Their crisp spiral arms and dense cores suggest gravity worked overtime, assembling cosmic cities in a fraction of the time our models allowed. But how some theorists whisper about dark matter behaving differently in the early cosmos, perhaps more sticky or prone to clumping, while others wonder if Einstein's equations need tweaking under extreme conditions. Then there's the enigma of the sparkler galaxy, surrounded by globular clusters that by all rights shouldn't exist yet. Its very existence hints at gaps in our understanding of star formation, as if the early universe had a secret recipe for building complexity we've yet to decode. The hunt for population 3 stars, those mythical first-generation giants made purely of hydrogen and helium, has become astronomy's white whale. Webb's detection of ancient gas clouds with bizarre chemical signatures suggests these stellar pioneers lived fast and died violently, seeding the cosmos with heavy elements before vanishing without a trace. Yet their direct light remains elusive, hiding in the noise of the cosmic microwave background or masquerading as distant quasars. Some researchers are chasing shadows in Webb's deep field images, looking for telltale patterns in the way these stars' supernova might have heated surrounding gas. Others are betting on gravitational lensing to magnify a lone surviving population 3 star, frozen in time like a fly in cosmic amber. Dark matter's role grows stranger with every observation. The way early galaxies cluster points to dark matter forming intricate webs far sooner than simulations predicted. Yet some galaxies rotate as if this invisible scaffolding is missing entirely. Could dark matter interact with itself through unknown forces, or might it decay over time, leaving voids where its gravitational grip once dominated? Webb's measurements of galaxy motions during the cosmic dawn, a period when dark matter's influence was paramount, are starting to reveal inconsistencies. One leading hypothesis suggests dark matter might have been warmer in the early universe, its particles moving fast enough to resist clumping on small scales, which would explain why dwarf galaxies are rarer than expected. Then there's the puzzle of the universe's missing ingredients. JWST has confirmed that ordinary matter, the stuff of stars, planets, and people, accounts for barely 15% of what gravity tells us should exist. The rest, a cosmic blank space in our equations. Some of this hidden matter might lurk in faint gas filaments too diffuse to emit light, while other portions could be tied up in exotic particles that barely interact with anything. Webb's ability to map the cosmic web structure through gravitational lensing is slowly filling in this ledger, but every new survey seems to add as many questions as it resolves. The greatest lesson from JWST isn't just how much we've learned, it's how little we truly understand. Each breakthrough peels back another layer of cosmic mystery, revealing complexities we never imagined. Those early galaxies, those ghostly stars, that invisible dark matter, they're not just puzzles to solve. They're reminders that the universe is far stranger, far more inventive than our boldest theories predicted. And that's what makes astronomy endlessly fascinating. The more we see, the more we realize there's left to discover. The universe isn't just for professional astronomers thanks to NASA's open data policy. The James Webb Space Telescope's breathtaking discoveries belong to everyone. From high school students to retired engineers, amateur scientists worldwide are diving into JWST treasure trove of images and spectra, uncovering cosmic secrets with nothing more than a laptop and curiosity. Platforms like the Barbara A. Mikulski Archive for Space Telescopes massed host raw and processed data, often within hours of observation, letting anyone sift through the same pixels that leave astrophysicists speechless. Take the story of a German biology teacher who spotted an overlooked gravitational lens in Webb's deep field images, a distant galaxy warped into a perfect Einstein ring by an intervening cluster's gravity. Or the amateur spectroscopists who analyzed light from exoplanet atmospheres, flagging unusual chemical ratios that later made it into peer-reviewed papers. These aren't exceptions, they're proof that cosmic exploration has democratized. Tools like NASA's FITS Liberator transform Webb's raw data into editable files, while citizen science projects like Zooniverse guide newcomers through classifying galaxies or hunting for supernova in crowdsourced projects. For those who prefer visual exploration, the Space Telescope Science Institute's JWST feed delivers near real-time images, often with interactive sliders comparing Hubble's and Webb's views of the same target. Want to inspect the pillars of creation at different infrared wavelengths? A few clicks let you isolate emissions from dust, hydrogen, or complex hydrocarbons. Online planetariums like ESA Sky even overlay Webb's observations onto 3D cosmic maps, revealing how that glowing nebula fits into our galaxy's spiral arm. The real magic happens when these tools collide with human creativity. Astrophotographers reprocess Webb's data to highlight subtle structures, like the faint tendrils of gas around dying stars. Educators build lesson plans around Webb's exoplanet spectra, letting students play detective with atmospheric chemistry. Even artists dive in, using the telescope's colorized mosaics as inspiration for paintings and music, turning cosmic data into cultural touchstones. This openness isn't just generous, it's strategic. By inviting millions of eyes to scrutinize every pixel, NASA taps into collective intelligence. An algorithm might miss an oddball galaxy with unusual star formation, but a curious human browsing mast on a lunch break could spot it instantly. The result, a virtuous cycle where professionals and amateurs collaborate, each discovery fueling the next. Whether you're measuring redshifts with open-source software or simply marveling at Carina Nebula's cliffs in 4K, Webb's greatest legacy might be proving that the cosmos doesn't belong to telescopes, it belongs to anyone willing to look up. JWST has done more than capture stunning images. It has handed us a new origin story for the cosmos. Every dataset from this telescope reads like a page from the universe's diary, scribbled in the faint glow of ancient starlight. Those galaxies that defied expectations by appearing too mature too soon, they're not just outliers, they're proof that the early universe operated on a different rhythm, one where gravity, dark matter, and star formation danced to a tempo we're only starting to decipher. And those swirling chemical signatures etched into primordial gas clouds, they reveal a universe that wasted no time forging the ingredients for planets and perhaps life, long before Earth even existed. What makes JWST discoveries so exhilarating isn't just their scientific value, it's how they redefine our place in the grand narrative. Staring at a galaxy that flourished when the universe was a toddler, we're not passive observers, we're the universe's way of looking back on itself. Every atom in our bodies, every breath we take, traces back to those early stars and the cataclysmic explosions that scattered their remains across space. The telescope's images aren't just snapshots of the past, they're mirrors reflecting our own cosmic lineage. Yet for all we've learned, JWST has magnified how much remains unknown. The Hubble Tension, those bafflingly mature galaxies, the ghostly whispers of population 3 stars, these aren't just puzzles to solve, they're invitations to rethink physics itself. Could dark energy evolve over time? Did black holes seed galaxy formation instead of the other way around? Each question JWST raises stretches the boundaries of our understanding, proving that the universe is far stranger than our boldest theories predicted. The most thrilling realization, this is just the opening chapter. JWST mission is far from over, and every new observation has the potential to append another assumption. Future telescopes Roman, Louvre, and beyond will build on its legacy, probing deeper into cosmic dawn and perhaps even glimpsing the very first flickers of starlight. But for now, JWST stands as humanity's ultimate time machine, bridging 13 billion years to connect us with the universe's infancy. So the next time you look up at the night sky, remember, you're not just seeing stars. You're witnessing a story that began in fire and chaos, a tale of transformation written in light and shadow. JWST hasn't just shown us where we came from, it's reminded us that we're part of something vast, ancient, and endlessly mysterious. The cosmos is still speaking, and its greatest secrets are yet to be told.